Hey guys, how's it going? This is Mike coming back at you with another video on discrete mathematics. In the previous video, we got a little bit of an introduction into sets, a certain special relationship between two sets, and we saw some samples as to when that may or may not happen and the various cases we can have. In this video, we are going to continue on with some special relationships between two sets. And we're going to get into a lot of very common sets that we'll see later on in this course, as well as in future math classes if you go on to take them. So something I meant to include at the end of the previous video, which I forgot to do. If you have two sets A and B, we say that A equals B, and we just write A equals sign B. If and only if every element that is in A is in B, and also every element that is in B is also in A. And what is that in terms of subsets? Saying A equals B is saying the same thing as A is a subset of B and B is a subset of A. Having a set be a subset of some other set, and then having that set be a subset of the first set, there's only one thing that can possibly happen. Those two sets have to be the same thing. And we'll encounter that. And how would we formally prove that? We're going to encounter that later on in this course. Now we come to some more special types of sets that come about as a result of two sets A and B. We're going to see these guys a lot, again, not only in this course, but in subsequent math courses as well. Most mathematics happens in some context. There's sort of an implied set of numbers that we are working in when we solve problems or when we solve problems of a particular type. The first and foremost case in point, most operations that we do in calculus, in linear algebra, any sort of more computational mathematics-based course, we are sort of implicitly working in the set of all real numbers. We're working in the set R. And whatever this context set is that we're working in is called the universal set or the universe of discourse. And we can give it the name capital U, or just U. So the following definitions are based on two sets A and B, and these sets are subsets of this universal set U. First up, the union of A and B. The union of A and B, and that is denoted by A, and then a small uppercase U, a small in size uppercase U, is the set of all elements that are in this universal set U, such that X is in A or X is in B. It can be in both, but how would we write this as a set? Using that familiar set notation, we'd write it as the set of all X in U, such that, again, that's what that big vertical bar there means, such that X is an element of A or X is an element of B. This is comparable to the disjunction of two statements P and Q in figuring out whether or not the disjunction is true or not. As long as one of the things is true, then the disjunction is true. As long as one of the guys is in A or B, then this guy is in the union of A and B. Similar to the conjunction of two statements P and Q, the intersection of A and B, and this is denoted by A, and then an upside down small size capital U, like a cup almost. It's cupped down. This is the set of all elements that are in this universal set U, such that X is in A and X is in B. So for an element to be in the intersection of A and B, it has to be in both A and B. As I said, similar to the conjunction of two statements P and Q. The P and Q both have to be true in order for the conjunction to be true. 3, the difference of B and A, or saying B minus A, is also known as the relative complement of A in B. But you'll just see me for the most part using the notation for it, the mathematical notation for it, which is B minus A. It's the set of all elements that are in this universal set, such that X is in B and X is not in A. So writing that as a set, B minus A is the set of all X in U, such that X is in B and X is not in A. Very shortly, we'll be coming to some more visuals to see what these things are actually saying and how these things make sense. And then fourth, the complement of A, which is denoted by A with a little c in the upper right-hand corner. It's the set of all elements that are in this universal set that are not in A. And so that is the set of all X in U such that X is not in A. That is a righto. There we go. Set of all X in U such that X is not in A. So here's a really basic sample here. Let my universal set be 1, 2, 3, 4, 5, 6, 7, and 8. And then I have my sets A, which are 2, 6, and 8. And then my set B, which is 1, 2, 4, 5, 7, and 8. The union of these two sets, we're going to take any guy that shows up in at least one of these two sets, and we're going to write all those guys in their own set. So we have 1, which comes from B, 2, which is in both A and B, but we only write it once. 4 comes from B, 5 comes from B, 6 comes from A, 7 comes from B, and 8 is in both A and B, but again, we only write it once inside of a set. So that's our union. Those are all the guys that are in either one of or both of A and B. Next up, the intersection of A and B. What guys are in both of these sets? Well, they both contain 2 and they both contain 8. So we put those guys inside of set brackets, separate them with a comma, and that is the intersection. Next up, the difference, B minus A. What are all the guys in here that are not in here? Okay, so 1 is in B and it's not in A. So that is a member of the difference set. That is a guy in B minus A. 2 is in B, but it's also in A. So that is not part of our difference set. And following on with that pattern of checking, 4 is in B, not in A, belongs in our difference. Same thing with 5. Same thing with 7. And then 8. 8 is in B, but 8 is also in A, so it does not belong to our difference. And then the complement of A. What are all the guys that are in U that are not in here? What are all what are all the guys in here that are not in here? Well, 1, 2 is in A, so that's not good. 3 is not in A. 4 is not in A. 5 is not. 6 is. 7 is not, and 8 is in A. So 1, 3, 4, 5, and 7 are all the elements in A complement. So this is just one nice, really low-level sample here, just to see how we would find these sets. Here are some visuals to help us see those in terms of Venn diagrams. The rectangle represents the universal set U. Inside of there we have two circles, one for the set A and another one for the set B. The shaded areas represent the special sets that we just talked about. Here, shaded area is A union B, the guys that are in at least one of those two sets. Over here, A intersect B is the set of all guys that lie in both of those sets simultaneously. Third one here, the difference set, capital B minus capital A, or B minus A, all the guys that are in set B that are also not in set A. So we're omitting that overlap there. We're omitting the intersection of those two sets. And then fourth here, A complement, just all the guys that are in U that are not in this set A. Okay, so next thing I want to talk about is a special set, and particularly pertaining to the intersection of two sets A and B. Sometimes there is a set that has no guys inside of it. Sometimes there is a set with no elements. This is a special set. We call it the null set, or it's called the empty set, and we have a special symbol for it. And you'll see it written two slightly different ways. You'll either see the letter O or something like a letter O with a slash through it, or you'll see the number 0 with a slash through it. But they look close enough to the point where you would understand that you're talking about the null set or the empty set. It's just the set that has no elements in it whatsoever. And here is one example of having a null set or having an empty set. Say I have the two sets 5, 3, and 4, and then the other set contains 1, 6, 8, and 10. If I try to take the intersection of these two sets, well, there's no element that lies in both of these sets at the same time. And neither set or both sets don't have a 1, a 3, a 4, a 5, a 6, an 8, or a 10. Both sets don't have any one of those guys in them at the same time. So this is a case where the intersection, if we call this, say we call this set A, and say we call this set B, this is a case where the intersection is the empty set or the null set. And this leads us nicely into our next definition. If you have two sets, A and B, that don't have any elements in common, that is to say, if you have two sets A and B, such that their intersection is the empty set, then we say that these sets, are disjoint. So if two sets don't have any elements in common, A, their intersection would be the empty set, and B, we would say that they are disjoint sets. Related to specifically two sets being disjoint, if we are working with more than two sets, we can talk about things being mutually disjoint. So say we have several sets, A1, A2, A3, A4, all the way up to and including AN. We say that these sets this collection of sets are mutually disjoint if and only if no two sets, AI and AJ, with different subscripts. So we're saying like A2 and A4, or A1 and A8, obviously not choosing the same set. So if and only if no two sets that have different subscripts have any elements in common. Equivalently, what we're saying here in a more mathematically notated way is that whenever I is not equal to j, A sub I intersect A sub j is going to give you the empty set. So here's a really basic low-level sample here to illustrate sets being mutually disjoint. A1 is the set containing 1 and 2. A2 is the set containing 3 and 5. A3 is the set containing 4 and 7. A4 is the set containing 6 and 10. And A5 is the set containing 8 and 9. If I were to pick any two distinct sets here, and I tried to take their intersection, I would get the empty set in every possible case. Give me A1 and A3, A5 and A4, A2 and A3, A1 and A5. Every possible choice of two sets, if I take their intersection, then I would get the empty set. Another way to say mutually disjoint, saying a group of sets is mutually disjoint, another way to say that is that amongst all sets, there are no elements in one set that are common to an element in any of the other sets there. So we see there are no repeats in these 5 sets here. Taking that definition of a group of sets being mutually disjoint, take that, combine it with one other property, and we get what's known as a partition. If we have a collection of sets that are mutually disjoint, and this collection is such that when you take the union of all these guys, you get this set, and we'll label it just capital A, then we say that this collection of sets, which we put inside of set brackets and separate them by commas, we say that this is a partition of our set capital A. Equivalently, these sets A1 through AN form a partition of a set capital A if and only if A equals the union of these A sub i's. A1 union A2 union A3 union all the way up to and including AN. And the A sub i's, these guys making up your partition, are all mutually disjoint. Just a couple more sets that I just want to introduce you to here at the end of this video, but don't worry too much with them at this point. Just want to at least show you them so you're not completely lost if you see these in a future math course. The next set I want to introduce you to is actually quite interesting. It's actually a set of sets. And if you think back in the previous video, when I was talking about when you use the element symbol versus the subset symbol, I said that if you have things that are enclosed in set brackets, it's going to be a subset with a certain exception. This is now that one special case where it's not necessarily a subset. The power set of a set A, which we denote by fancy P of A, is actually the set of all subsets of A. So here's a really basic sample. Take the set A, which just has the numbers 1 and 2. A subset of capital A here is the subset just containing 1. Another subset is just the set containing 2. Those are 2 separate subsets of A. By definition, every set is a subset of itself. So A is a subset of A. Also, by definition, the empty set or the null set is a subset of every set. So P of A here, notice that all the guys that are separated by commas, which are the elements of this set, all these guys are on their own subsets of A. So this is where the set gets really confusing. It's totally normal to be confused by this, so don't worry with it. We're not working too much with it in this course. I just want to show it to you. But this is the power set of A. It is the set of all the subsets of the set capital A. How would you know how many elements should be in this set? If your given set A has n elements and you're asked to find the power set of A, then the power set of A is going to have 2 to the power n elements inside of it. So A here had 2 elements to it, so I knew that the power set of A was going to have 4. And then the other set here, the Cartesian product, given sets A and B, the Cartesian product, which is denoted by A times B or A cross B or A x B, is the set of all ordered pairs such that the first guy in that ordered pair comes from the first set, namely capital A, and the second guy in your ordered pair comes from the second set, namely capital B. How would we write this as a set? A cross B is the set of all things of the form A comma B inside of parentheses, such that little a is from capital A and little b is from capital B. So here's a really basic sample here. Let A be the set with 1, 2, and 3, and B be the set with 4 and 5. So I'm going to start with 1. I'm pulling that from my set capital A. Then I'll take 4 from my set capital B and make that the second number listed in my ordered pair. So 1 comma 4, that is 1 element in my Cartesian product. I can then take that 1 once again, and then I can take 5 from B, and that will form another ordered pair. And I can keep going through with this same process. Pick a guy from A, pick a guy from B, make those the first and second listed numbers in your ordered pair. You have an element of your Cartesian product. How would you know how many elements are in this set? Well, if A has m elements, and if B has n elements, then A cross B will have m times n guys. There. M times n guys there. So this is the wrap up of our second video here on the introduction to set theory stuff, special sets that we get as a result of 2 sets A and B. In the next video, we'll be doing several practice problems, helping ourselves get more comfortable with finding sets like the union or the intersection or the difference or the complement, things like that. If you have questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.